This is a really interesting technology. This is a company called Osmotex, which was acquired by Myant, and they make, you can think of it as a textile that you apply a small voltage and you can actually pump water. So think of a jacket that dries the sweat off the small of your back as you're trekking to the Alpines, but also think of a wound dressing that keeps the hydration of an ulcer at the right levels to promote healing. So this core technology of leveraging multiple pieces of call it fabric, and we can see some demos over here, but in clever ways, this is a solid state pump. It's a sheet of, multiple materials, but this you apply a voltage to and it'll actually move water. And so by integrating this into textiles, as you can see here, you can have really interesting properties. So this is Spencer here. He's one of our engineers, and he's going to show us how this technology works.
I'm a chemical engineer working here in material science research, and specifically this is one of the projects that I work on where we look at transporting water across solid surfaces and using it for different applications. Here we just have a simple power supply here providing a really low voltage, below 1 volt. And we have an assembled panel here, so we have a couple different iterations, so like some coated samples, some laminated samples. So I'll show you the big laminated one here. And the idea here is that these assembled layers have a certain technology inside them, membrane technology that will transport water with a slight, very low, like I said, applied voltage. So low applied voltage, you should be able to see the water transport here. So yeah, the nice thing about this is that it's all assembled in one piece, and it's like a 2D film. So you can see here, I'll just apply a bit of water on the surface so you can get a sense of how this looks. So you can see some water being passed through. And you can see it's quite fast. So I'll show you that this isn't just simple penetration into a textile. This is something else, right? So now when I switch the leads, that's the drying effect, and this is the re-wetting effect. So now you can see the water coming back up to the surface, sort of like magic. But it's really just the assembly and the way that this is made allows for this to happen.
Difference here is it's not just like a university working on some technologies and we have a few pictures and some publications. We're working closely with the people that make the products right after. And having them integrated in the development cycle really changes the time frames from when you have an idea to when you have a product. And the idea that everybody's working together, so at the same time we're trying to figure out how to make a panel that might go in a jacket, we're working on what are the suppliers and the performance like for this, electrode material, or what if we do it like this? Would this solve maybe some of the requirements from the jacket or garment manufacturer? So having that back and forth and that real integration for productization and development is really what changes, kind of the approach of how we work on things here. So what's really interesting about this technology is it also works in the vapor phase. So when you think about, what's interesting about the vapor state, well, all of a sudden you can start to affect humidity. You can start to reduce and pump out water vapor from one environment to another. At a small scale, this is really interesting for maybe optoelectronic assemblies, think lasers and guidance systems, those kind of things that need to maintain a dry environment regardless of temperature fluctuations. But you can also think of it on a huge scale. So industrial dehumidification is a huge industry, and as it should be, because it's one of the primary paths to lower energy usage is stop, spending so much energy to control comfort through temperature and indirect dehumidification and start directly applying dehumidification, especially as parts of the world warm at different rates. The humidity is going to be one of the major driving forces towards comfort and environment. So if we can have an effect on that in a solid state manner with this technology, it's one of the big goals of this project beyond transporting liquid is being able to transport vapor. This is a bunch of engineers informing the scientists what needs to be captured, what data needs to be collected in those initial experiments, so that it's not just, it worked, but how did it work? How does it interact with other systems? So again, the complication that is apparent here is really a result of that integrated approach. We are making sure the experiments we do generate the information, which enables us to maybe do development in a leaner manner, or also maybe more in an agile manner. So less, searching for new advancements, more having a direct targeted approach on what needs to be solved and how to solve it. All right, so we're in our print lab. We're one of the many print labs now. And so, here you can see, we can start with this filament printing. So this is, you might be familiar with this type of 3D printing. It's a bigger version of what you might have at home as kind of a hobbyist filament printing. What we use it for here is printing composite piezo sensors. So this was a project we did with the National Research Council of Canada, the lab across the parking lot there. We worked on the problem statement, say, if you've got a lot of wind turbines, let's say, in areas prone to icing and snow, how can you detect ice buildup? So one of the solutions that we identified is if we can make conformable piezo sensors. So these are sensors that can be printed on curved surfaces, and almost like a microphone and a speaker together, they can send out beeps and listen to hear if there's ice on the surface. And if they are, you can report back to give different preventative maintenance outcomes to that piece of equipment. The result of that is less helicopter flyouts to northern, areas of the environment, less safety incidences, and more kind of economics directly focused on maintaining the assets with the minimum intervention. We can see other equipment in here. Again, a lot of our, as much as our approach is multiple disciplines, our labs are multiple capabilities. So these are a collection of capabilities towards the same outcome. So we've got ultrasonic spray coating. You might be doing catalyst spray coating when you're working on your CO2 reduction, your hydrogen generation. You may be spraying on advanced materials in creating batteries, right? And this is a technology that's very, it can do things that others can't. So we saw the slot die coater in the other lab. That will give you a certain set of properties. This will give you a certain set of properties. Having both of them here, when we work through ideas to test out how are we going to make this stuff at scale, is so important. So again, that flexibility capabilities is what allows us to turn those interesting ideas into products. One of the technologies that we worked on previous to the acquisition was a powderization technology. Okay, so this is, again, if you're going to have a bunch of the smart people in the marking space and they think, okay, what's the next marking material? What's the next consumable in the material space? And one of the things that was identified was 3D printing. So this is actually a powderization technology that's targeted at powder printing, industrial powder printing. So what we did is we approached the problem to say, okay, what are the limitations holding back the industry or the approach right now? One of the major limitations, and we can see here, is that the current materials, the materials you might make a shoe out of, right? The soft materials are all cryo-ground. That leads to very jagged particles. When they're jagged, they don't flow well, especially when they're soft. So that limits how soft of a material you can print. That limits what kinds of shoes you can design, because the materials that you might use for an injection molded or a foamed shoe aren't available in 3D printing. So we saw that as the biggest opportunity. And we said, okay, if we develop a new technology to turn any pellet into any powder, that will enable us to cross that threshold. And so you can see the process is very simple. It starts with pellets here, and it goes with a silicone oil, and it's dispersed, and you end up with a dispersion of silicone oil and powder. And what you get is very fine flowing powder. So that's interesting for a multitude of reasons, because you can get really good properties. You see, in terms of DPI, when they pack very tight, when they're round, not only are they stronger, but you can take red and white and start mixing them, and your eye can't tell that it's composed of two different colors. And that's a direct result of how closely the packing is. So you can do interesting things. Again, this is, might look like a party trick of multiple colors, but all of a sudden, if you can offer this as a product using only two base materials, it has a real impact. Here we can see a bunch of compliant, full color, small particles. We've even got, glow in the dark to demonstrate that you can put anything in or on the particles, right? And that can be really interesting. We're interested in this technology now from a controlled release perspective. So we can use the same technology to create particles with active pharmaceuticals in them. And by affecting the surface morphology and the coatings, we can control the rate at which they release their dosages. So we talked a little bit earlier about drug delivery and how personalized medicine won't just collect your information, but start to provide outcomes. One of the ones that we feel is important is the drug outcome. So understanding how your body's interacting with itself and in the environment, and changing or modifying the dosage of drugs. So having a platform material that is able to control the rate of release is a really important foundation there. Ed's probably been involved indirectly or directly in at least half of those 3,000 patents we talked about earlier. But here he is working on what's called the factory of a box. So this is multiple operations in a single box. So you can do pick and place, you can do paste extrusion, you can do milling, etching, all these kinds of things, and you can make integrated circuits. and prototype multiple processes all in one. So Ed's using this to start to prototype devices for a biosensor area of work. So we're going to start looking at what does a sensor that measures cortisol not just one day but over weeks look like, and how does a person interact with that sensor in terms of wearability, and what is the shape and how does the function of it. All of these questions can be answered by prototyping on something like this.
Cardiovascular disease around the world is still growing, still the leading cause of death, notwithstanding the advancement of AI or the knowledge of doctors or the many good doctors. We're no longer in 1940. There are a lot of good doctors. So the question one needs to ask is why cardiovascular disease hasn't gone down. It's not because lack of knowledge or lack of AI, it's the lack of relationship between us on a continuous basis with AI and with our doctors. So with our solution, number of clinics right now are using it. A patient don't have to shave, they don't have to put adhesive patches, they don't have to sleep with wires, all of these unfamiliar things. They just wear a bra, an underwear, a tank top, a polo, a chest band, and they just go about their life. And instead of returning the product after 3-4 days, they can keep it for a year or two or forever. And now they start understanding relationship and experiences they may go through with evidence of their EKG. So now when they talk to their doctor next time, they can say, doctor, you know, 2 Saturdays ago, I was dizzy. I didn't feel well. Because we tend to always converse like this with doctor. We talk to them in the past, but we have no evidence to confirm. So the doctor said, okay, let me issue you a device for the future. And the doctor hoped that to catch what you complained about. I don't believe in that model. In our model is, since people are wearing underwear, bra, tank top, in this example, if I use the same example in our own reality, you call the doctor, and the doctor will be able to go back retrospectively to that 2 Saturdays or 3 Saturdays, and he or she will see your EKG, your blood pressure, your O2 and know exactly what's going on with you without the need of you going and booking an appointment, etc. And we're already approved with Health Canada. So all billing is happening. We qualify for reimbursement from the government. So our product is designed for those kind of things. So we're growing pretty fast. So Myant, when we met last year, is developing and scaling up and producing every single day more and more product. Myantx is the new business we acquired. It's a fascinating business, but we have a massive ambition. Where we see an addressable market of billions and billions of people, and we want to consolidate and displace the needs of having standalone devices in our everyday life, specifically in medical devices for now.
This is for printed electronics. So this facility was actually one of the pioneers, or the pioneer, wrote the seminal paper in printed electronics. So that's how do you print inks made of metals or conductive elements to make circuits on surfaces that aren't, copper-clad laminates or PCBs. So we built on that, over the years, but, this is an example of a multitude of technologies working together to develop, kind of a system level approach. So this isn't just silver ink. The silver ink used here has a very low sintering temperature. So that means, mostly silver is hundreds and hundreds of degrees to melt. If you have small enough particles, you can actually get it to melt maybe around 120 or 160 degrees Celsius. That difference in 120 or 160 degree is so important, because when you can do 120, you can print on things like cardboard. When you can do 120, you can start to develop systems that maybe ship to someone as an experienced flat pack, but then can be assembled. And this can be a multitude of materials working in tandem here. We've got flexible interconnects, we've got solder pastes, we've got dielectric materials for vias. So there's a lot of different materials going on here, and this was culminated in a project where we looked at how do we make a new experience with point of purchase display. So starting to print sensors to determine if let's say a product's been interacted with on a point of purchase display to give a certain experience to a client. So this core foundational technology is something that we're also going to continue to leverage in our biochemical sensing platforms. So now we're entering what we might call the textile pilot plant, right? So this is a set of machines that are used, not just for light production, but also for prototyping new concepts. So again, when we talk about the importance of having the development happening so close to the production, this is again an example of that. So this is the same machines that we use, on a much larger scale to produce the products. These are also used to determine, what's the next type of conductive filament we're going to use? How does it wash not just 50 times, but 100 times? How do we improve the ECG signals while someone's, doing vigorous exercises? These are all types of innovations that we can test having the production capabilities here. And so you can see here production of one of the bands. This is exactly how it comes off the machine. So you can see how powerful that is. The electrodes are already integrated, all of the interconnects. There's a simple cut and sew at the end to get the pod there, and this is it. So that's really the heart of the Myant technology, is having that textile computing platform, being able to design the textile to have all of that intelligence, or the capability for intelligence within it.
Just imagining the idea of a textile that can speak, that can feel, a textile that can send, take info, send info, give some heat, probably cold as well. Imagine a textile that can do anything for you. And if you do not want to wear it, you can sit on it, sleep on it. Would you imagine the world in 5 years? And remember, you're watching today a video, a documentary, saying usually what inside this factory is never filmed. And you're going to remember it in at least 5 or 10 years from now.
This is the hidden gem. This is what you don't find anywhere else. So the idea being, how do you build a plant without knowing what you're going to make in it? That's a very odd question, right? I'm going to make a plant to do inks. I'm going to make a plant to do tires. I'm going to make a plant to do mattresses, whatever. The idea that you can have a plant with any kind of capability. You can have a plant, you want to test any kind of process, you can do it in one location. That really gives your scientists and engineers the freedom to develop new ideas without the constraints of, can we actually make a product if successful? So when we talked about open innovation, this is the key here. This is what's holding back hard tech. I mean, software, 2 people in a garage can create a company that's infinitely scalable. When you're making materials, there are assets involved. There are timescales, and you think of all of the great ideas coming out of universities and research. The reason it takes so long is because they generally have to acquire these kinds of assets. Not just these kinds of assets, but the people to run them and their experience. Our pilot plant operators most of them have over 20 years experience. So they're researchers in the process with them, right? So when we can take that money that would have either been spent, time and money, on acquiring new capital and acquiring new people, if you can take that instead and putting it right to demonstration, to prove to the accountants you want to build this plant because it'll make money, that's exactly what we do here. So Anthony, you might be asking, what is this? Is this a giant Rube Goldberg, or is this an engine machine? So what this is a collection of capabilities. It's a bunch of reactors. So if you want to make, we started the advent, you think of color toner, how impactful that was in the world. That kind of core technology that enabled better resolution printers, nicer magazines, nicer, bigger colors, more material innovation that started here and developed through this pilot plant. So made sure all of the processes worked before we went and spent, $100 million or so and built an actual plant to produce it. That's a big jump, right? So by having this here, we were able to de-risk that. We were able to convince people, yes, it will work. It has worked and it will work. Now, what we're using this capability for is the next generation. So you think of, what can you do with this series of capabilities? You go from making photoreceptors. Well, what happens when there's less printing? Well, we work with partners that make, let's say, cathode patterning materials. So when you think of the transparent OLEDs at CES that you see last year, you'll see them for the next, however many years. The core technology that enables that are materials like OTIs that we produce in this plant. So having that range of capabilities is demonstrated by being able to not just be relevant to the printing industry, but being relevant to the new crop of advanced material innovation. You know, everything from micro bead replacements. So microplastics are a huge industry, I mean, huge issue. We worked with a company doing crystalline nanocellulose that actually has a product to enable cosmetic manufacturers to formulate without microbeads. So you've got the same plant. You go from making toner to making OLED type materials to making, you know, cellulose nanoparticles that will enable the cosmetic cream that you buy in the future to be microbead free. That's all a materials connection. That's all not just dreaming of what could be, but actually demonstrating that it can be and showing what it looks like as a product. So Anthony, you might have noticed half of this place looks like a university and half of it looks like a factory. That's really important and done on purpose. So the idea of having everything in one location, you know, the same people that make it in 500-gallon reactors and tiny little test tubes play cards with each other at lunch. That's how you really make impactful innovation. And you really need that full service. So it's one thing to have an idea and to make it, but what if you want to test it? So even things like a machine shop like this, I mean, these machines might look old, but they are enabling cutting-edge fixtures. So cutting-edge fixture development to say, you know, we want to have a new yarn coating machine, you know, like working on different types of systems to enable the testing of new materials. You've got to have everything in-house in order to turn it around quickly.
This center was created almost 50 years ago as a captive corporate research center for Xerox Corporation, working in advanced materials to develop the materials that go into the printing business. But the reality is that deep tech can apply to any business, and it's what underlies all different valuable technologies that are on the market today. And as a result, our expertise in advanced materials can be applied to many different things, and in this case, including textile computing. So this center is now the research arm for our new core technology, which is textile computing, but it does continue to offer services and research and development in the area of advanced materials deep tech.
One of the few videos where I'll be speaking in English. I'll be speaking in English for the world to know, for the world to watch, for the world to see. I met this amazing person a year and a half back. He had a dream, the dream of building the future, the dream of writing the future, and that dream grew way bigger in a year and a half only. A new building, a new company, X added to Myant. Myant is something way bigger than you might imagine. Myant is writing your future today. And Tony, proudly Lebanese, has started in Lebanon, had a dream in Lebanon, I would say woke up from death, and then arriving in Canada, is shaping the world and shaping the way we see the future of medicine and the future of fabrics.
Over here we have a demonstration of where we begin in developing the smart textiles, and that starts from the materials development. So the fibers, the yarns that are used for the functionalization of fabrics, and in essence creating a textile circuit board that will kind of constitute the smart textile features. We begin from the core components, and you probably saw a background of our chemical and material science expertise, from the raw polymers that can turn into fibers, and those fibers that we create are proprietary to our requirements and different applications, and we can translate those into, as you can see here, examples of electrodes, electrophysiological electrodes that can capture electrical signals, bipotential electrical signals from the body, such as an electrocardiogram for monitoring of cardiovascular health. And this process has been a very systematic and scientific approach towards fine-tuning the polymer, getting it to turn into a fiber, building that into a functional textile, and then pairing that with the electronics or the bioinstrumentation that acquire the signals from the smart textiles, and how we integrate the electronics with those textile components into a textile circuit board, and we can in essence create a equivalent of a medical device within a textile context. Once we have the function established, then we go into the form, ensuring that the product or the technology can be productized for the user base and individuals in need, taking into consideration the comfort, the ability for this to be unobtrusive and easy for people to use. So example of which, elderly populations that might have some challenges with dexterity. How would they put it on? How would they take it off? And is it easy for them to use and to remember to keep this as part of their daily habits and routines? So then we go through that product development and looking at our customer base, both on the user side of those individuals wearing the textiles, but also on the side of individuals that will be digesting the data and aiding those individuals in their healthcare journey. As we go about our daily life, we're constantly beaming data that is being uncaptured. The thesis and the purpose of Skiin is to capture that data and provide that data back to the individual in a actionable manner such that they can digest it, utilize it, and use it for a variety of purposes. Our primary goal is for healthcare and longevity and allowing individuals to take care and control of their own care, and not only their own, but also managing their loved ones. So as you can see here, if we imagine a family, they are wearing different Skiin products, from a bra to an underwear to a tank top and to a chest band for a baby. So every member of the family can wear a certain form factor depending on their comfort, depending on the application, whether they're going to do athletics, whether they go to sleep, or whether they're at home or at work, to capture this data and create this understanding, this continuous understanding of what is happening with them and how they're going about, akin to a dashboard of a vehicle. So when we get into a vehicle, we turn it on, we know what's going on with the gas, we know the heat, we know the battery level, the fluids, and all that jazz. Why don't we have that for an individual? As we saw, the Skiin flagship product is around cardiovascular disease monitoring, but our system is bidirectional. And what that means is we not only sense and monitor, but we also provide actionable insights to the individual, or responsive that are autonomous through the smart textile platform. So over here we have a demonstration of an actuation, which is functional electric stimulation. So individuals that might have been affected by a stroke or a spinal cord injury have some deterioration in their motor function and have some muscle atrophy. Over here we're demonstrating through those same textile electrode the ability to create a sleeve form factor for upper limb retraining of individuals with a stroke or a spinal cord injury, or also lower limb training. So depending on the level of injury that you have, depending on what level of therapy you need, this system can kick in. Now this system not only provides the stimulation, but also captures the joint locations, it captures the kinematics, and it is a closed loop system within the textile structure, providing that therapy to the individual. So what this will enable, now individuals that require this therapy have to go to a clinic, which would be very arduous for them due to their injury, having the time from the clinician or the care provider to give them an hour for the therapy. And if they have the means to do that 3 days a week, 3 times a week, that's great. But in this context, they can go home with this system, decouple that, and provide these services outside the brick and mortar of a hospital service, and they can do it as much as they desire, and they can track their own improvement, and they can basically manage their own therapy, and the insights and the data from them doing these sessions will also be shared with their coach and care provider, so they won't kind of have a blind spot as to what they're doing, if they're kind of complying with the protocols and what they're being prescribed, and they can also provide them insights as they're going through their care and rehab journey. Another use case where we have deployed our smart textile technologies is around electromyography, or capturing the activity of the muscles. Over here we're demonstrating a wristband that can capture the muscle activities of the forearm, and we've demonstrated it initially as a game where through the contraction of your hand you can basically activate a game and jump. And this was a very preliminary demonstration, but the system had around 16 pairs of electrodes capturing finer motor functions. Then what we did, we went one level deeper into training the AI or the algorithms that are embedded on the system to do certain functions, such as hand close and hand open for a robotic arm, using flexion and extension of the forearm. So again, initially we were building the sensory to make sure that it's viable. Then we went to go one level deeper to add a degree of freedom instead of just jumping, to be open and close. And then we went to the extent of doing fine motor function, because we did have the necessary sensors in place to capture the fine motor function with the 16 electrodes, or 8 pairs of electrodes. And over here we paired the finger functions, and we applied a algorithm that would detect those hand functions. And this was the initial model. That was the updated one, as you can see from the mechanical arm and hand that becomes a lot more refined, where we trained the model into detecting and programming the certain finger functions of the individual. And this was personalized. And then after it was trained, then we applied it to the robotic arm, and all those would be replicated and played in real time. And this system that we're demonstrating here is currently in use, and we are working with a partner that is a prosthetics company in deploying it and providing it to their user base. And just to put that in perspective, currently individuals that would like to have controlled prosthetics usually use metallic pins or like the back of a screw that contacts their arm and captures those biopotentials. And as you can imagine, over time, that is pretty invasive and abrasive to the skin, preventing the continuous use of them, especially if you're picking up a load and how that would dig into your skin. With our textile form factors, this would be a much more, I guess, user-friendly and interface-friendly option.
I'm the inventor of the Osmotex electro-osmotic textile technology. So this is the first technology to transport electronically liquid but also vapor across a textile membrane and a textile laminate. It works, it's also unique in that it can provide this going in one direction forever, unlike some others which just pumps back and forth. So this is for garments, for clothing. Think of a jacket like Gore-Tex but 100 times bigger transport and protecting you for protective clothing, but it's also for medical application like wound dressing and other cases where you want to either remove sweat, moisture for your skin, maybe for samples, maybe for comfort, and also if you want to pour something to the skin like a drug delivery system.
Spread on 3 floors, there's someone working or developing something all across. Labs, and more labs, and more labs. Technology, from mechanical machines all the way up to the latest technologies, spread on 3 floors, hundreds and thousands of square meters. There's someone working and developing the future we know today.
At Myant, we are fostering the development of the ecosystem needed to transform the way people connect to and interact with the physical and digital world. Healthcare and the Myant Health Division is the first area we are deploying this new platform for human connection.
Currently right now, Myant Corp is the parent company, consists of at least 4 unique companies that enable the possibilities that we have at Myant Corp. So at Myant Corp, it's all about enabling a culture where human, or a society where human, AI, IoTs, and animal can coexist in harmony in a sustainable society. So I happen to believe innovation is an element of making. And the more you make, the more you innovate, because some of that innovation is happening during the act of making. So Myantx is really essential for us. Myant Health is the result of that research, and Myant Health is a company that will promote longevity. And of course, longevity for us is really important, is longevity for all, whereby we want to develop this ongoing and continuous relationship between one and their health by making it so convenient for people to have continuous guidance. Myant Venture is a new company that we set up, and the point of that company is to provide some of our financing to third-party companies, startups, industry that want to develop their idea, as long as that idea is in the same kind of ecosystem, the same kind of a platform, the same vision, the same direction. we're willing to finance startups or a mature company to go the distance. And of course, we can not only can take their idea and validate it and progress it using our process that meets TRL 1 to 9, we can also accelerate their funding and their requirement and help them in their commercial strategy. And then Myant Animal Science is a new division, and I did that actually for my wife and for my daughter because my wife is an equestrian and my daughter have the same passion. So my life is a challenge. If I decide to go on a holiday or decide to do something spontaneous, it's almost mission impossible. So I felt, okay, how do I connect animals on a continuous basis to my family and to their vets? So this way, if I decide to go away, at least if something is wrong with the dog or something is wrong with the horses, then we can live in peace and we can do whatever we want. So kind of the same idea, but for animal.
Some of the things I was allowed to film and some other things not. But remember, I'll be back, probably in a year or two, filming again and again the future of medicals, paramedicals, and technology. I wish I can tell you more. I wish I can tell you more.